Before we begin, a quick disclaimer. The information provided in this video is for educational purposes only and should not be considered a substitute for professional advice from a licensed mechanical engineer, a certified kitchen ventilation specialist, or your local authority having jurisdiction. Codes and regulations, including those from the NFPA, IMC, and local health and fire departments, vary significantly by location and are subject to change. Always consult with qualified professionals and your local officials to ensure your project is compliant and safe. Failure to do so can result in catastrophic fire, financial loss, and legal liability. The single most expensive mistake you can make when opening a restaurant has nothing to do with your menu, your location, or your staff. It's a mistake that can shut you down before you ever serve a single customer. A mistake that turns a six-figure investment into a smoldering pile of debt. And it all starts with a simple piece of stainless steel hanging over your cook line. I'm talking about your commercial kitchen hood. Imagine this. It's the final inspection. The culmination of months, maybe years of planning, building, and dreaming. The fire marshal walks in, clipboard in hand. He's not looking at your beautiful decor or your state-of-the-art ovens. He walks straight to the kitchen, looks up at your brand-new gleaming hood system, and pulls out a pressure gauge. He shakes his head. He points to a seam that isn't fully welded. He asks where your makeup air unit is ducted, and your contractor just shrugs. Then he slaps a big red tag on your system. You have failed inspection. Your grand opening is canceled. The clock is now ticking on your rent, your payroll, and your loan payments, all while your kitchen sits cold and silent. This isn't a scare tactic. This is a Tuesday for thousands of restaurant owners across America. They get sold the wrong hood, or a contractor who normally does residential HVAC tries to install it, and the entire project grinds to a halt. This video, this entire series, is your insurance policy against that nightmare. We are going to pull back the curtain on the secrets of commercial kitchen ventilation, from selection and installation to the maintenance that keeps you safe and profitable for years to come. We're going to give you the knowledge to ask the right questions, to spot the red flags, and to hold your contractors accountable. You will learn how to navigate the alphabet soup of codes, NFPA 96, IMC UL 300, and understand why they exist. By the end of this, you won't just be buying a hood, you'll be investing in the heart and lungs of your entire operation, and you'll be doing it right the first time. So, why is this so complicated? Why can't you just hang a metal box with a fan and call it a day? Because a commercial kitchen hood is not an appliance. It is a life safety system. It's an integrated engineering marvel designed to do one primary thing: control and contain a fire. Everything else, the removal of heat, smoke, and grease-laden vapor, is secondary to that primary mission. Think about it. You have multiple open flames, fryers filled with 375-degree oil, and charbroilers hitting over 600 degrees, all generating vaporized grease. That grease is fuel. It gets sucked into the hood, coats the inside of your ductwork, and collects on the fan blades on your roof. All it takes is one flare-up on the grill, one small spark, to ignite that grease trail. Without a properly designed, installed, and maintained system, that spark becomes a duct fire, a blowtorch ripping through your building at 2,000 degrees Fahrenheit. That's why the codes are so strict. That's why the welds have to be liquid tight. That's why the fire suppression system has to be integrated perfectly. It's not about convenience, it's about preventing a total catastrophe. But the danger isn't just fire. The financial fallout from getting it wrong is just as devastating. Let's talk about the silent killer of restaurant profits: negative air pressure. A typical 12-foot kitchen hood can exhaust over 4,000 cubic feet of air per minute. That's like sucking all the air out of a small apartment every 60 seconds. If you don't replace that air with a proper makeup air unit, or MUA, you create a powerful vacuum inside your building. What does that feel like? It feels like your front door is impossible for customers to open. Feels like your pilot lights on your water heater and ovens keep blowing out. It means your HVAC system is fighting a losing battle, trying to heat or cool a building while the kitchen hood is actively sucking all that conditioned air straight out the roof, sending your utility bills into the stratosphere. It means carbon monoxide from your gas appliances, which should be going up the flue, gets pulled back down into the kitchen, creating a toxic environment for your staff. These aren't minor annoyances. They are fundamental operational failures that all stem from a poorly designed ventilation system. And the costs just keep piling up. You buy the wrong type of hood, say a Type 2 condensate hood for a fryer, and the inspector will make you rip it out and buy the correct Type 1 grease hood. That's $10,000 down the drain. plus the cost of the new hood and reinstallation. Your contractor installs ductwork with screws instead of liquid-tight welds? Tear it all out. It's a massive fire hazard. The fan is undersized for the length of the duct run and the appliances underneath? You'll never capture the smoke effectively. Your kitchen will be a miserable place to work, and you'll fail your inspection. Over the next 10 parts, we're going to break this all down. We're going to start with the absolute foundation, understanding the difference between a Type 1 and a Type 2 hood, and how to know exactly which one you need for every single piece of equipment on your cook line. Get this first step wrong and literally nothing else matters. We'll cover how to calculate the exact amount of exhaust air, or CFM, your kitchen requires. We'll dive deep into the unsung hero of every functional kitchen, the makeup air unit. We'll walk through the critical components of a fire suppression system. We'll explain what to look for in a contractor, and the key questions you must ask before you ever sign a contract. And finally, we'll cover the essential maintenance and cleaning procedures that keep your system running safely and efficiently, satisfying the fire marshal and your insurance company year after year. This isn't just about avoiding disaster. It's about building a smarter, safer, and more profitable business from the ground up. The secrets we're about to share aren't taught in culinary school, and most contractors won't walk you through them. But understanding them is the difference between a grand opening and a grand closing. So let's get started. The very first decision you'll make is also the most unforgiving. Get it right and your kitchen breathes. Get it wrong and your business suffocates. We're talking about the hood itself. And no, they are not all the same. Thinking a hood is just a hood is like thinking a rowboat engine will power a battleship. It's a catastrophic and shockingly common mistake. To understand this, you need to see your kitchen not just as a room with appliances, but as a living, breathing organism. The cooking line is the heart, pumping out heat, energy, and your culinary creations. But the ventilation system, the hood, the ducts, the fan, that is the lungs. And if the lungs fail, the heart stops. In the world of commercial kitchen ventilation, there are two fundamentally different species of hood, and choosing the wrong one is like trying to make a fish climb a tree. It's not just inefficient, it's a violation of the laws of nature and the fire code. First, you have the heavyweight champion, the one everyone pictures, the Type 1 hood. This is your grease warrior. Its entire reason for existence is to capture what the industry calls grease-laden vapors. Imagine a burger hitting a hot charbroiler. That sizzle, that smoke, that incredible smell. It's not just smoke. It's an aerosolized cloud of vaporized fat, water, and tiny food particles. As this cloud rises, it cools. And when it cools, that grease turns back into a sticky, highly flammable liquid. A Type 1 hood is an integrated system designed to fight this battle. It has a series of grease filters, baffles typically, that act like a maze. As the greasy air is pulled through, it's forced to make sharp turns. The heavy grease particles can't make those turns. They lose momentum, slam into the stainless steel, and drip down into a collection tray. What gets through is mostly just hot air. But that's only part one of its job. The Type 1 hood is your first line of defense against the #1 threat in any restaurant: a grease fire. It's legally required to have a built-in fire suppression system, with nozzles aimed directly at your appliances, ready to douse a flare-up in an instant. This isn't just a piece of metal. It's a firefighter, standing guard over your most valuable assets 24/7. If you are cooking with anything that produces grease and smoke, fryers, griddles, charbroilers, ranges, a Type 1 hood is not a choice. It is the law. Then you have its cousin, the Type 2 hood. This is the steam tamer. A Type 2 hood is designed for heat and moisture, not grease. Think about the massive cloud of steam that erupts when you open a commercial dishwasher, or the dry heat pouring out of a convection oven when you're baking bread. That's what a Type 2 hood is for. It's a condensate hood. It collects water vapor and funnels it away, keeping your kitchen from turning into a tropical rainforest. It has no grease filters. It has no fire suppression system. It is, in essence, a much simpler and cheaper piece of equipment. And that price difference is a siren song for unsuspecting entrepreneurs. Let me tell you about a guy we'll call Frank. Frank wanted to open a small gourmet pizza and sandwich shop. He had a top-of-the-line deck oven for his pizzas and a small flat-top griddle for his cheesesteaks. He saw the price for a full Type 1 system and his stomach dropped. Then he saw a Type 2 hood online for a fraction of the cost. He thought, it's an oven and a small griddle. How much grease can there really be? So he bought the Type 2. For the first month he felt like a genius. He'd save thousands. But then the problems started. A sticky yellow film began to coat the ceiling and the walls near the oven. His cooks started complaining that their eyes were always burning. The smoke alarm, which he'd placed just outside the kitchen, went off during every dinner rush, sending customers a very clear signal that something was wrong. The final straw came during his first health inspection. The inspector took one look at the greasy buildup inside that Type 2 hood and the ductwork beyond it, and shut him down on the spot. He explained to Frank that he hadn't just installed the wrong hood. He had built a fire trap. That grease buildup was pure fuel, a wick running from his cooking line straight to the roof. Frank had to close his brand new restaurant for 3 weeks, rip out the entire system, and install the Type 1 hood he should have bought in the first place. The money he saved was vaporized, along with his profits and his reputation. Frank's mistake was thinking all hoods were the same. But even within the world of Type 1 hoods, there are different designs for different jobs. The most common is the wall-mounted canopy. It's the workhorse you see in 90% of kitchens, hanging over a line of equipment pushed up against a wall. Simple, effective, and efficient at capturing the rising plume of smoke. But what if your equipment is in the middle of the room, like a show kitchen or a large island prep area? That's where you need an island canopy, sometimes called a double island canopy. It's essentially 2 wall canopies placed back to back, creating a giant inverted funnel in the center of the kitchen. It has to be bigger and more powerful because it doesn't have a wall to help contain the smoke. It's capturing it from 360 degrees. Then there are the more specialized, low-profile hoods. You might see a backshelf or proximity hood. These are small, boxy units that sit much closer to the cooking surface, often just inches above a countertop charbroiler or griddle. They're designed for situations where a massive overhead canopy would be overkill or would block the chef's view. They work on the principle of close capture, sucking the smoke and grease away horizontally before it has a chance to mushroom up into the room. So how do you know which one is right? This is the secret inside the secret. The decision isn't based on the hood. It's based on the appliance underneath it. Professionals classify cooking equipment by duty level, which is just a fancy way of asking, how much grease and heat is this thing going to produce? There's light duty. Think steaming vegetables or boiling pasta. Lots of moisture, very little grease. This is the easiest to ventilate. Then there's medium duty. This is your workhorse diner equipment. Gas ranges, flat-top griddles, small fryers. They produce a moderate amount of grease and a significant amount of heat. Next up is heavy duty. Now we're talking serious firepower. Charbroilers, upright broilers, woks. These appliances operate at incredibly high temperatures and throw off a massive amount of grease particulate. The smoke plume is violent and hard to contain. And finally, at the top of the mountain is extra heavy duty. This is reserved for one thing: solid fuel. We're talking wood-fired pizza ovens, charcoal grills, anything that burns wood, charcoal, or briquettes. The grease from the food combines with creosote from the burning fuel to create an exceptionally stubborn and flammable residue. These systems require specialized hoods and pollution control measures because the smoke is so intense. Why does this matter? Because the duty level of your appliance dictates the power of your kitchen's lungs. It determines the airflow measured in cubic feet per minute, or CFM, that your exhaust fan will need to pull. A light-duty steamer might only need 200 CFM. A heavy-duty charbroiler could need 1000 CFM or more for the same amount of space. Choosing the right type of hood is step one. But matching it to the duty level of your equipment is the master key. It ensures you're capturing everything you need to, without spending a fortune on an overpowered system you don't. You could have the most beautiful, expensive, perfectly chosen stainless steel hood in the world, a true work of art. But it is just a useless hollow box without the right engine doing the hard work. And that engine, the exhaust fan, is where almost every single major, costly, business-destroying mistake is made. It's a component most people never even see, hidden away on the roof. But its type, its size, and its placement will determine whether your million-dollar kitchen investment actually works, or just makes a lot of noise while your kitchen slowly fills with smoke. That rooftop fan is the unsung, unseen hero of your entire kitchen. It's the engine. It's the heart that pumps the lifeblood of the system. Get it wrong and everything else fails. The most common mistake we see, the one that costs restaurant owners tens of thousands of dollars in lost revenue and emergency repairs, is treating this fan like an afterthought. It starts with a simple, seductive thought. A fan's a fan, right? Let's just get one that moves enough air. That single assumption is the seed of a nightmare. Let's talk about that engine. Not all fans are created equal. The most common type you'll see on a roof is a centrifugal upblast exhaust fan. Imagine a wheel spinning incredibly fast, grabbing the greasy air from your kitchen, and flinging it straight up, high into the atmosphere away from your roof. This design is brilliant for a few reasons. First, by blasting the exhaust upwards, it prevents that nasty corrosive grease from just pooling on your roof, eating away at the membrane and causing leaks. Second, these fans are designed with a grease trap, a small container that collects the heaviest grease particles that condense and drip down, preventing them from running back down the ductwork. It's the standard for a reason. It's effective, relatively simple, and it protects your building. But what if you can't put a fan directly on the roof above your kitchen? Maybe you're in a multi-story building and the kitchen is on the first floor. This is where you might see something called a utility set fan. These are heavy-duty, powerful blowers that can be mounted on the roof, on the ground, or even inside a mechanical room. They're connected to the ductwork and are designed to handle long, complex duct runs with lots of bends. They can pull air from much farther away than a standard upblast fan. The trade-off? They're more expensive, more complex to install, and often louder. They're a solution for a specific engineering problem. Then you have the real problem solvers. Inline fans. These are fans designed to be installed directly inside the ductwork itself. You use these when you have absolutely no other choice. Think of a historic building where you can't penetrate the roof in a convenient spot, or a design where the duct has to run horizontally for a long distance before it can go up. The fan gives the air an extra boost along its journey. But be warned, inline fans can be a maintenance catastrophe if not installed perfectly. Since they're inside the duct, they are swimming in a river of grease. They need to be meticulously sealed and have proper access panels for cleaning, because a grease-caked inline fan is not only a massive fire hazard, it's a ticking time bomb for failure. Now, knowing the types is one thing. Sizing the fan is where fortunes are won and lost. This brings me to a client we'll call David. David was opening his dream barbecue joint. He'd sunk his life savings into it. Custom smoker, beautiful build-out, the works. He got a quote for his ventilation system, and the contractor specified a big, expensive exhaust fan. David's cousin, a handyman, looked at the specs and said, "Whoa, that's overkill. You can get a fan with the same CFM for half the price." CFM stands for cubic feet per minute. It's a measure of air volume. So, to David it sounded logical. If fan A moves 4,000 CFM and fan B moves 4,000 CFM, but fan B is cheaper, why wouldn't you choose fan B? So he did. He saved $3,000. The restaurant opened. For the first 2 weeks it was a disaster. The dining room was constantly hazy with a light film of smoke. The kitchen was unbearable, with temperatures soaring. His cooks were miserable, threatening to quit. The smoke alarms went off twice during service. He called his handyman cousin, who had no idea what was wrong. "The fan is running, I can hear it," he said. The problem wasn't the CFM. The problem was a force that most people have never heard of: static pressure. Let me explain. Imagine you're trying to drink a very thick milkshake. If you use a short, wide straw, it's easy. You don't have to suck very hard. Now try drinking that same milkshake through a coffee stirrer, one of those tiny little red straws. You'd have to suck so hard your cheeks would cave in. You might not even be able to get any milkshake at all. The amount of suck you need to generate is the static pressure. In a kitchen ventilation system, the air is the milkshake. The fan is your mouth, and the ductwork is the straw. David's barbecue joint had a long, complicated duct run. It went up, made a sharp 90-degree turn, ran 30 feet horizontally, then made another 90-degree turn before going out the roof. Every single foot of duct, every single turn, every filter the air has to pass through, is like making that straw narrower and longer. It adds resistance. The cheaper fan David bought could indeed move 4,000 CFM in a perfect world with no resistance, what we call free air, like using that short, wide straw. But it was a low static pressure fan. It didn't have the muscle, the sucking power, to pull that 4,000 CFM of heavy, smoky air through his long, winding, high-resistance duct system. The expensive fan his original contractor specified was a high static pressure fan, an engine built specifically for that long, difficult journey. The fire marshal came in for a routine inspection, saw the hazy conditions, and immediately shut him down. David was losing thousands of dollars every single day he was closed. He had to pay for a new high static pressure fan. He had to pay for a crane again to lift the old fan off and put the new one on. He had to pay for an installer again. That $3,000 savings ended up costing him over $30,000 in lost business and rework. The fan is not a standalone part. It is the heart of a system, and it must be engineered to handle the unique resistance of your specific system. The calculation involves the size of your hood, the type of cooking you do, the exact length of your ductwork, and the number and angle of every single elbow. It is complex engineering, not a guessing game. Anyone who tells you they can just look at a kitchen and pick a fan is either a liar or an amateur. Finally, even with the right fan properly sized, its placement on the roof is critical. You would be horrified to know how many times we've seen an exhaust fan installed right next to the building's fresh air intake for the HVAC system. The kitchen fan blasts out hot, greasy, smoky air, and the HVAC unit happily sucks it right back in and pumps it into the dining room. Your customers get to enjoy the lovely aroma of old grease and smoke with their meal. It's an instant business killer. Code dictates minimum distances from air intakes, property lines, and adjacent buildings for a reason. And just as important is accessibility. The fan must be installed on a proper roof curb, and it absolutely must have a hinge kit. This is non-negotiable. This allows a technician to tilt the fan open for cleaning and service, instead of having to lift the entire heavy motor assembly off the duct. It's a safety feature that protects the technician and a cost-saving feature that protects your wallet during routine maintenance. A fan without a hinge kit is a nightmare to clean properly, which means it often doesn't get cleaned properly, leading to grease buildup, imbalance, motor failure, and worst of all, fire. So we have the perfectly engineered fan, sized for static pressure, placed correctly on the roof. The engine is ready to roar. But the most powerful engine in the world is useless if the transmission is shot. And in this system, the transmission is the ductwork, the steel arteries connecting your hood to that fan. And how those arteries are built and sealed is the difference between a safe, effective kitchen and a ticking time bomb hidden in your ceiling. That ticking sound isn't an exaggeration. A single and properly sealed joint in your grease duct, hidden above a drop ceiling or inside a wall chase, is one of the most insidious and dangerous failures you can have in a commercial kitchen. It's a silent threat. Grease-laden vapor doesn't just stop when it finds a pinhole. It's under pressure, forced by the fan. It will find that escape route. It seeps out atomized and hot, coating everything it touches, wooden studs, insulation, electrical wiring, with a fine flammable layer of fuel. Day after day, week after week, that fuel load builds up, unseen and unknown, until one small spark turns your building's hidden spaces into a raging inferno. The fire doesn't start in the kitchen. It starts in the ceiling 10 feet away, and by the time you see smoke, it's often too late. This is why the construction of your ductwork isn't just a matter of connecting point A to point B. It's a matter of absolute, uncompromising containment. And it all starts with the right material. For grease ducts, the code is crystal clear. You use steel, specifically carbon steel or stainless steel. You will never ever see galvanized steel used for a grease duct. And if you do, you are looking at a catastrophic failure waiting to happen. The reason is simple chemistry. The zinc coating on galvanized steel reacts with the fatty acids in grease and the chemicals used for cleaning. This reaction can flake off the zinc, but more importantly, it creates a combustible residue. You're literally building a fire hazard into the system. The standard is typically 16-gauge black steel. Think of gauge as the thickness of the steel. The lower the number, the thicker and more robust it is. 18-gauge, which is slightly thinner, is sometimes allowed, but 16-gauge is the workhorse. This thickness isn't just for show. Its primary purpose is to contain a fire. If a fire does start inside that duct, the steel needs to be thick enough to hold its shape and integrity at incredibly high temperatures, preventing the fire from escaping into the building long enough for the fire suppression system to do its job. A flimsy duct will warp, buckle, and tear open, rendering the entire fire safety system useless. But having the right material is only half the battle. The real secret, the detail that separates the pros from the cowboys, is how those pieces of steel are joined together. The code, specifically NFPA 96, which is the Bible for kitchen ventilation, mandates one thing above all else. All seams and joints must be liquid-tight. And there is only one way to achieve a truly liquid-tight seal on steel ductwork: a continuous weld. Let me say that again. A continuous weld. Not stitch welding where you have a series of tacks. Not spot welding. Not using high-temperature silicone or foil tape, which is a horrifyingly common shortcut we see. And absolutely positively not using screws. Every single inch of every seam must be welded shut, creating a seamless monolithic steel tube. Why such an extreme requirement? Because hot grease behaves like water, it will find the tiniest gap. A stitch weld leaves microscopic gaps between the stitches. A screw creates a hole. A gasket can fail over time. A continuous weld, done properly, makes the joint as strong and impenetrable as the steel itself. The duct becomes a sealed vessel, ensuring that every last particle of grease makes it from the hood to the exhaust fan on the roof, with zero chance of escape along the way. When an inspector runs their hand along a seam, they're feeling for the smoothness of a continuous bead. When they shine a light inside, they're looking for any pinprick of daylight that signals a leak. It is a pass or fail test with no room for error. This brings us to the cardinal sin of ductwork installation: screws. You cannot use any fasteners that penetrate the duct walls. Period. Not only does each screw create a potential leak point for grease to escape out of the duct, it also creates a problem inside the duct. Think about it. The inside of that duct is supposed to be as smooth as possible to promote airflow and make cleaning easier. Every screw tip that pokes through to the inside becomes an anchor point. Grease as it flows by snags on that screw tip. Over time, more grease builds up on that initial deposit. It solidifies, cools, and hardens. Soon you have a grease stalactite forming inside your ductwork. This not only restricts airflow, forcing your fan to work harder and reducing the effectiveness of your hood, but it also creates a concentrated chunk of fuel. These grease deposits are notoriously difficult to remove during cleaning and represent a severe fire hazard. A proper system is smooth on the inside, a sealed tube with no interruptions. Now let's talk about where this sealed tube goes. You can't just run it anywhere. This duct is carrying flammable residue at high temperatures, so you have to keep it away from anything that can burn. This is called clearance to combustibles. The rule of thumb dictated by code is an 18-inch clearance. That means there must be at least 18 inches of empty airspace between the outside of that grease duct and any combustible material. And what's considered combustible? Pretty much everything a building is made of. Wood studs, joists, plywood sheathing, even the paper on the back of drywall. In a new construction with plenty of open space, achieving this 18-inch bubble is straightforward. But in a tight retrofit, in an old building with crowded ceilings, finding 18 inches of free space can be impossible. So what do? You can't just ignore the rule. This is where one of the most important innovations in kitchen fire safety comes in: fire-rated duct wrap. This isn't just insulation. This is a high-tech blanket, typically made from ceramic fiber, that is specifically tested and listed for this exact purpose. You wrap the ductwork according to the manufacturer's strict specifications, usually 2 layers with overlapping seams, all held in place with steel bands. A properly wrapped duct system is a game changer. It effectively insulates the combustibles from the heat of the duct. It's rated to withstand a 2000-degree Fahrenheit internal fire for 2 hours. This rating means that if a fire is raging inside the duct, the outside surface of the wrap will not get hot enough to ignite the wood joist that is right up against it. This technology allows you to reduce that 18-inch clearance down to 0 in many cases, letting you safely route a duct through the tightest of spaces. But it has to be installed perfectly. Any gap, any improperly overlapped seam, and the entire system's fire rating is void. Finally, we have to address the reality of maintenance. We've built this incredibly robust, continuously welded, perfectly sealed steel tube. How on earth is anyone supposed to clean it? You can't send a person crawling through a 24-inch duct. The answer is access. Code requires approved access panels to be installed at critical points. You need one at every change of direction because grease, being heavy, tends to accumulate on the outside of turns. You also need them on any long horizontal run, typically at a maximum of 12-foot intervals. And these aren't just simple metal plates screwed onto an opening. That would violate the no penetration and liquid tight rules. A proper UL-listed grease duct access door is an engineered piece of hardware. It has a high-temperature gasket that creates a seal, and it uses a system of clamps or bolts on the outside of the door to press it firmly into place, ensuring a leak-proof fit without penetrating the duct wall itself. This allows cleaning crews to open the system up, get their tools inside, and scrub the ductwork from top to bottom, then seal it back up to its original liquid-tight integrity. Without these access panels, effective cleaning is impossible, and an unclean duct is just a vertical fuse waiting to be lit. So you see, the ductwork is far more than just a tube. It's a high-performance containment system, engineered to transport a dangerous, flammable byproduct safely out of your building. Every weld, every inch of clearance, every access panel is a critical link in a chain of safety. If any one of those links is weak, the entire system is compromised. So you have a perfect hood and perfectly sealed ductwork. But all of it is useless without the heart of the system, the engine that creates the suction. And that engine sitting up on your roof has its own set of secrets that can make or break your entire operation. And that engine is your exhaust fan. It might look like a simple metal mushroom on your roof, but it is the single most critical mechanical component in your entire ventilation system. Get this part wrong, choose the wrong model, install it incorrectly, or neglect its maintenance, and it doesn't matter how perfect your hood or ductwork is. Your kitchen will fail. It's not a matter of if, but when. Let's start with the biggest, most expensive mistake people make right at the beginning. Choosing the wrong fan. You see, not all fans are created equal. You'll primarily encounter two types: the direct drive fan and the more common belt drive fan. A direct drive fan has the fan wheel connected directly to the motor shaft. It's simpler with fewer moving parts, which means less maintenance. The downside: the speed is fixed. You get what you get. The belt drive fan, however, is the workhorse of the industry. The motor is separate and uses a belt and a system of pulleys, or sheaves, to spin the fan blades. This is brilliant because it allows you to fine-tune the fan speed by changing the pulley sizes, giving you precise control over the airflow. This is absolutely critical for balancing the system, a concept we'll dive into later. But with more moving parts comes more responsibility. But the type of drive is only the first decision. The real secret is understanding the relationship between CFM and static pressure. Everyone gets obsessed with CFM, cubic feet per minute. It's the raw volume of air the fan can move. A bigger number seems better, right? Wrong. That's like saying a car with a 200-mile-per-hour speedometer is fast, without considering the engine. The engine, in this analogy, is the fan's ability to overcome static pressure. Static pressure is the resistance your fan has to fight against to move that air. Every foot of ductwork, every 90-degree elbow, every filter in your hood, it all adds resistance. It's like trying to breathe through a very long, winding straw. You can have a fan rated for 3000 CFM in a perfect open-air test environment, but if it can't handle the static pressure of your specific duct run, you might only be getting 1500 CFM in reality. Your kitchen fills with smoke, your staff is miserable, and you have no idea why because you bought a 3000 CFM fan. The secret is that a professional ventilation designer doesn't just pick a CFM number. They calculate the total static pressure of the system and select a fan specifically engineered to deliver the target CFM against that specific resistance. It's a surgical decision, not a shopping trip. And for kitchens, there's one more non-negotiable detail. The fan must be UL 762 listed, meaning it's specifically built to handle grease-laden vapor. It's constructed to contain a grease fire for a period of time and to allow grease to drain properly. Installing a standard ventilation fan, like one you'd use for a bathroom, over a commercial cooking line isn't just a bad idea. It's a massive code violation that will get you shut down by the fire marshal in a heartbeat. Now let's assume you've selected the perfect fan. The installation is where champions are made and failures are born. It all starts with the roof curb. This is the raised metal frame the fan sits on. Its primary job is to keep water out of your building. A poorly installed curb, one that isn't properly flashed and sealed into the roofing material, is a guaranteed leak. It might not happen the first month, but after a year of baking in the sun and freezing in the winter, that cheap sealant will crack, and you'll be paying for ceiling repairs, mold remediation, and a new roof. The secret is to treat the curb installation with the same respect as a skylight. It has to be an integral, waterproof part of the roof system itself. Next up, the hinge kit. Listen closely. A hinge kit is not optional. NFPA 96 code mandates that fans be installed on hinges. Why? For cleaning and service. Without a hinge, the only way for a hood cleaner to access the ductwork in the underside of the fan is to lift the entire, incredibly heavy fan assembly off the curb and set it on the roof. This is dangerous for the technician, and it almost always damages your delicate roofing membrane. Every single time it's lifted, you risk creating a new leak. And worse, it puts immense strain on the electrical conduit. I've seen live wires get severed by a fan being carelessly put back down. A hinge kit allows the fan to be safely tilted back, giving full, easy access without ever breaking the seal of the curb or straining a single wire. If your installer says you don't need one, show them the door. And while we're up on the roof, let's talk about something that drives restaurant owners and their neighbors crazy: noise and vibration. These fans, especially the big ones, can create a low-frequency hum that can travel right through the building structure. It's maddening. The fix is incredibly simple and cheap: vibration isolators. These are small spring or rubber mounts that sit between the fan and the curb, absorbing the vibration before it can enter the building. It's a $50 part that can save you thousands in noise complaints and headaches. It's one of the most commonly skipped items by low-bid installers, and one of the most valuable secrets for a peaceful kitchen environment. Finally, we get to the heart of the fan, the motor and the belt. This is where ongoing maintenance becomes the difference between a system that lasts 20 years and one that dies in 2. That fan belt lives a hard life. It's under constant tension, spinning for hours a day in the blistering heat of a rooftop. It stretches, cracks, it wears out. The number one cause of a sudden, "My hood isn't working" service call is a snapped belt. A technician should be checking the belt tension and condition on every single service visit. A belt that's too loose will slip, reducing your fan speed and your exhaust performance. A belt that's too tight puts immense strain on the motor and fan bearings, leading to premature, catastrophic failure. It has to be just right. And that brings us to the bearings. Inside your motor and on the fan shaft are bearings that allow everything to spin smoothly. They require lubrication. Most motors and fan shafts have small grease fittings, called Zerk fittings, for this exact purpose. But here's the secret almost everyone gets wrong. You can't just use any grease. You must use the specific type of high-temperature grease recommended by the fan manufacturer. And you can't just pump it full of grease. Over-greasing can blow out the bearing seals, which is just as bad as under-greasing. It's a delicate procedure. Clean the fitting, add just the right amount of the correct grease, and run the fan to distribute it. This simple act, performed every 3 to 6 months, can literally double the life of your expensive fan motor. Neglect it, and you'll start to hear a faint squeal, which will turn into a grinding roar, and then silence. The silence of a seized motor and a $5,000 emergency replacement on a Saturday night. The fan on your roof isn't just an appliance. It's the breathing lung of your kitchen. Its selection requires a deep understanding of physics, its installation demands precision and an obsession with waterproofing, and its survival depends on a disciplined maintenance routine. You've now engineered the perfect system for pulling hundreds, even thousands of cubic feet of air out of your kitchen every single minute. You've created a powerful, consistent, and clean exhaust stream. But in doing so, you've also created a powerful vacuum inside your building. A vacuum so strong it can slam doors shut, starve your ovens of oxygen, kill your HVAC system, and even dangerously pull carbon monoxide back into your kitchen from your gas appliances. You've solved one half of the equation. Now we have to address the invisible and equally important other half. This invisible other half is called makeup air, and ignoring it is the single most common and most catastrophic mistake made in commercial kitchen design. A kitchen is a living, breathing thing. Your exhaust hood, that powerful fan we just spent all this time installing, is the exhale. A massive, powerful, constant exhale, blasting thousands of cubic feet of air per minute out of your building. But what happens if you only exhale? Try it. Exhale and keep exhaling. You can't. Your body instinctively screams for an inhale. Your kitchen is no different. When you suck that much air out, you create a powerful vacuum, a negative pressure zone. The building itself starts to gasp for air, and it will find it anywhere it can. It will pull air through the tiniest cracks in the window seals, creating a high-pitched whistle that will drive your staff insane. It will pull air from underneath the doors, creating drafts that chill your customers and send napkins flying off tables. It will make your front door feel like it's attached to a 100-pound weight, forcing your customers to fight their way in and your servers to struggle with every trip. In a worst-case scenario, that back door you use for deliveries, the negative pressure can become so strong it will slam that door shut with terrifying force the second you let go of it. But it gets far more dangerous than that. Inside the kitchen, this invisible force wreaks havoc. The flames on your gas range, which should be a steady, clean blue, will start to dance and lick outwards, starved for oxygen. Your pilot lights might flicker and die. And this is where it turns deadly. That vacuum doesn't just pull air from outside. It can reverse the flow of your other vents. Your water heater vent, your furnace flue. They are designed to send exhaust, including deadly carbon monoxide, out of the building. But a powerful, unbalanced kitchen hood can actually suck that poison right back in, silently filling the space where your team is working. This isn't theoretical. It's a documented, life-threatening reality. So how do we fix this? How do we let the kitchen breathe? The principle is beautifully simple. For every single cubic foot of air you exhaust, you must mechanically introduce 1 cubic foot of fresh, replacement air. This isn't a suggestion. It is the fundamental law of a balanced system. This replacement air is makeup air. It's the controlled, deliberate inhale that complements the hood's powerful exhale. But just like you wouldn't want to inhale freezing, dirty air, you have to be smart about how you introduce this air back into your kitchen. There are a few primary ways to do it, and the choice you make will have a massive impact on your energy bills and the comfort of your staff. The first and most basic is called untempered or unconditioned makeup air. This is the brute force method. A fan, a vent, and a filter on the roof pull outside air directly into the kitchen. In a temperate climate like Southern California, this can work just fine. But imagine you're in Chicago in January. It's 10 degrees below zero outside. This system will take that 10-degree air and blast it directly into your kitchen. Your line cooks will be freezing. The cost of heating your kitchen will skyrocket as your main furnace fights a losing battle against a constant stream of Arctic air. It's cheap to install, but you'll pay for it in employee misery and astronomical heating bills. That brings us to the next level: tempered makeup air. This is the smart play for most of the country. These makeup air units have built-in heaters, typically gas or electric. Before the outside air is introduced into the kitchen, it passes through this heating element and is warmed to a comfortable temperature, say 65 or 70 degrees. Yes, the unit itself is more expensive, and yes, it uses energy to heat the air. But the result is a comfortable kitchen, happier and more productive employees, and a building that isn't in a constant state of thermal warfare. This is an investment in your operation, not just a box on the roof. And for those in the hottest parts of the country, think Phoenix, Miami, Dallas, there's the top-tier option: fully conditioned makeup air. These units not only heat the air in the winter, but also cool it in the summer using DX or chilled water coils. When it's 110 degrees outside, the last thing you want is to pump more hot air into an already blazing kitchen. This system delivers cooled, dehumidified air, dramatically improving the working conditions and taking a huge load off your building's main air conditioning system. Now, we know what kind of air we're bringing in, but where we bring it in is just as critical. The placement of your makeup air diffusers can either help your hood or fight against it. The goal is to introduce the air without disrupting the capture envelope, that invisible curtain of air being pulled into the hood. If you blow makeup air directly down onto your cooking appliances, it will be like trying to have a conversation in a hurricane. Smoke, grease, and heat will be blown all over the kitchen before the hood ever has a chance to catch it. One of the most effective methods is using a perforated supply plenum, or PSP. This is often integrated directly into the front face of the exhaust hood itself. It looks like a panel with hundreds of tiny holes. The makeup air is gently pushed through these holes, creating a soft curtain of air that falls in front of the hood. This is brilliant for 2 reasons. First, it's not a harsh blast, so it's comfortable for the staff. Second, it actually helps the hood do its job. This air curtain acts like an invisible barrier, helping to contain the smoke and guide it directly into the exhaust filters. Another common method is using ceiling diffusers. These are the square or round vents you see in most office ceilings. The key here is strategic placement. You want them far enough away from the hood that they don't disrupt the airflow, but close enough to provide air to the area that needs it. A common strategy is to place them behind the cook line, so the fresh air flows across the chef's backs, towards the hood, and then gets pulled out. This creates a comfortable, effective airflow pattern. But here is the $1,000,000 secret: the piece of advice that will save you more money and more headaches than almost anything else we've discussed. You must, under all circumstances, keep your kitchen makeup air system completely separate from your building's main HVAC system. I see this mistake all the time. A contractor thinks they can save a buck by just tapping into the restaurant's main air conditioner to supply the makeup air. This is a recipe for absolute disaster. Your dining room HVAC is designed for comfort. It's meant to handle a predictable load: body heat, sunlight, a few lights. It moves a relatively small amount of air, slowly and gently. Your kitchen exhaust hood is an industrial monster. It's moving thousands of CFM with incredible force. Tying these 2 systems together is like asking a Prius to pull a freight train. You are asking your dining room AC to suddenly compensate for a wind tunnel that just opened up in the back of the house. It will fail miserably. Your dining room will get hot and stuffy because the AC can't keep up. The unit will run constantly, trying to fight a battle it was never designed for. Your energy bills will be astronomical. And eventually, the compressor on your very expensive HVAC unit will burn out, leaving you with a hot dining room, angry customers, and a 4 or 5-figure repair bill. The kitchen must have its own dedicated, properly sized makeup air system. It is a non-negotiable rule for a functional, efficient, and long-lasting operation. The systems are designed for two totally different jobs. Let them do them. So we have our exhale, the exhaust, and we have our inhale, the makeup air. They are perfectly balanced, a 1-to-1 ratio. The kitchen is breathing. The pressure is neutral. The doors open easily. The flames on the stove are steady. The carbon monoxide is going where it's supposed to, outside. We have created a safe, comfortable, and functional environment. We've built the lungs of our system, but lungs don't work without a brain. Next, we're wiring it all up and giving it intelligence, turning a simple fan and a vent into a smart, responsive, and automated system that saves you money and headaches. This is where the magic happens. This is the moment we give our mechanical beast a central nervous system and a brain. Because right now, what we have is a collection of very expensive, very well-installed parts. A powerful fan on the roof, a meticulously sealed duct run, a beautiful stainless steel hood. But without the electrical and control systems, it's just inert metal. It's a world-class athlete in a coma. We're about to wake it up. Now, for a lot of people, the word electrical is where their eyes glaze over. It seems like a dark art, a mess of colored wires and cryptic diagrams. But I want you to reframe that. This isn't just about connecting power. This is about choreographing a dance between the air leaving your kitchen and the air coming in, a dance between your cooking equipment and your ventilation, and most importantly, a dance between safety and efficiency. Get the choreography right, and your kitchen operates in perfect, profitable harmony. Get it wrong and you're left with chaos, high utility bills, and a system that's constantly fighting itself. Let's start with the heart of it all. The control panel. Think of this as the command center. It's not just a fancy on-off switch. It's the nexus where every critical function meets. Inside this box you have the high-voltage connections, the raw muscle, that power your exhaust fan motor and your makeup air unit motor. But you also have the low-voltage connections, the delicate signals that control the system's intelligence. This panel is what allows your line cook to walk in at 5 a.m., flick a single switch, and have the entire ventilation ecosystem spring to life in the correct sequence. Lights on, exhaust fan on, makeup air on. One action, a cascade of perfectly timed reactions. From this control panel we run our wiring. And this is not the time to cut corners. The wiring is the nervous system, carrying signals from the brain to the muscles. We run it through conduit, a metal pipe that acts as armor. Why? Because a commercial kitchen is a hostile environment. It's hot, it's greasy, it's wet. A standard unprotected wire would be degraded and destroyed in months, creating a massive fire hazard. The conduit protects these vital communication lines, ensuring they can do their job for decades. And one of the most critical signals these wires carry is for the interlock system. This is non-negotiable. It is a life safety requirement in every single jurisdiction. The interlock is the system's involuntary reflex. It's survival instinct. It connects your ventilation system directly to your fire suppression system, the tanks and nozzles located inside your hood. If a fire ever breaks out on the line and that suppression system is triggered, it sends an instantaneous signal to the control panel. What does that signal do? Two things immediately and without fail. First, it kills the power to the makeup air unit. You do not want to be pumping fresh, oxygen-rich air onto a grease fire. That's like throwing gasoline on it. Second, it simultaneously triggers a shunt trip breaker or a gas solenoid valve to cut off the fuel supply to all the cooking appliances under the hood. It starves the fire of fuel and oxygen. The exhaust fan, however, keeps running, pulling the smoke and the fire-suppressing chemicals up and out of the building. This isn't a feature you can opt out of. It's the system's ultimate fail-safe, and it has to work perfectly 100% of the time. So, we have power, we have basic controls, and we have our critical safety interlock. This is a functional, code-compliant system. But it's a dumb system. It's a flip phone in a smartphone world. It only knows two states, on and OFF. And when it's on, it's at 100% power all the time. Whether you're searing a dozen steaks during the Saturday night rush, or just simmering a single pot of stock on a quiet Monday morning, that fan is on the roof screaming at full blast, pulling a massive volume of conditioned, expensive air out of your restaurant. It's wasteful. It's loud. And frankly, it's obsolete. This is where we install the brain. We upgrade from a simple on-off switch to a true intelligent system. We do this by introducing demand control kitchen ventilation, or DCKV. It's a mouthful, but the concept is revolutionary and simple. Instead of running at full blast all the time, the system automatically adjusts its fan speed based on the real-time cooking load. How does it know? It has senses. We install specialized sensors inside the hood canopy. There are temperature sensors that constantly monitor the heat rising from the cooking appliances. There are infrared sensors that can detect flare-ups. And in the most advanced systems, there are even optic sensors that can literally see the density of smoke and vapor being produced. These sensors are constantly feeding data back to the brain, a more advanced controller, often incorporating a variable frequency drive or VFD. The VFD is a remarkable piece of technology that allows us to precisely control the speed of the fan motors. Think of it like a dimmer switch for a giant motor instead of a light bulb. Now let's put it all together and see what this intelligence actually looks like in a real kitchen. It's 10 a.m. on a Wednesday. Your chef is doing light prep work. Maybe one burner is on low, simmering a sauce. The old dumb system would be running at 100%, wasting a fortune in energy. But our smart DCKV system? The sensors read a low heat signature and see no smoke. They send a message to the controller. All quiet on the Western Front. The controller then tells the VFD to dial the exhaust and make up air fans down to, say, 25% of their maximum speed. The system is just whispering. It's saving electricity. It's saving your heated or air-conditioned makeup air. And the kitchen is significantly quieter. Then the lunch rush kicks in at noon. The charbroiler is fired up, the fryers are bubbling, all 8 burners on the range are blazing. Instantly, the sensors detect a massive spike in heat and see plumes of smoke and steam. They scream an urgent message to the controller. It's showtime. The controller processes this data in a microsecond and commands the VFD to ramp the fans up to 90 or 100% power. The system comes to life, creating a powerful vortex of air that captures every bit of that grease, smoke, and heat, and expels it safely from the building. The kitchen stays clear, the chefs stay comfortable, and the fire risk is minimized. As the rush subsides, the system senses the drop in cooking activity and automatically dials itself back down. It breathes with the rhythm of your kitchen. It's not just on or off. It is responsive, adaptive, and incredibly efficient. The energy savings here are not trivial. We are talking about reducing your fan energy consumption by 50 to 80%. Over the course of a year, that translates to thousands or even tens of thousands of dollars in savings, depending on the size of your operation. The system literally pays for itself. And the benefits don't stop there. By not running the motors at full throttle all day long, you dramatically reduce the wear and tear on the bearings, the belts, and the motor itself. This means a longer lifespan for your equipment and fewer costly emergency repair calls. It's like the difference between redlining your car engine everywhere you go versus driving it smoothly. Which car do you think will last longer? But here's the critical part that nobody tells you. Installing this smart technology is not plug and play. The final crucial step is commissioning the system. This is where a technician fine-tunes the sensors and programs the controller specifically for your kitchen and your menu. They set the baseline temperatures and the ramp-up speeds. They calibrate the optic sensors to ignore a little bit of steam but react instantly to a grease flare-up. Without proper commissioning, you've just installed a very expensive, very complicated on-off switch. It's the difference between buying a high-performance race car and actually having a professional driver tune it for the track. One is just potential, the other is a winner. So we've taken our system from a simple mechanical assembly to a living, breathing entity. We've given it a nervous system that's robust and protected. We've engineered its life-saving reflexes through the fire suppression interlock. And we've installed a sophisticated brain that allows it to think, sense, and adapt, saving you an enormous amount of money in the process. The machine is built. The intelligence is online. It's ready. But there is one final test. One gatekeeper who holds the power to approve all our hard work, or shut us down completely. We've built the perfect system on paper and in practice, but now we have to prove it. Now we have to pass the inspection. And that is a battle of details, where one loose wire or one missing label can mean the difference between opening your doors and being trapped in a nightmare of delays and revisions. The inspector isn't your enemy. Let's get that straight. But they are the gatekeeper. They are the final guardian standing between your investment and your grand opening. Their job is not to be your friend. Their job is to find the one thing you missed, the one corner you cut, the one detail that could, under the worst circumstances, lead to a catastrophe. They are walking onto your site with a rulebook, the International Mechanical Code, the NFPA 96 local amendments, and they are looking for any deviation no matter how small. Your job is to give them nothing to find. Absolutely nothing. This is where the professionals separate themselves from the amateurs. It starts the day before the inspector is scheduled to arrive. This is your dress rehearsal. You need to become the inspector yourself, and you need to be 10 times tougher than the real one will be. First, you assemble the Bible. This is a binder, and inside it is every single piece of paper related to this project. The stamped and approved mechanical plans, the manufacturer's cut sheets and installation manuals for the hood, the fan, the makeup air unit, and the fire suppression system. Your permits. Everything. When the inspector asks for a document, you don't say, I think it's in my truck. You open the binder to the correct tab and hand it to them. This one small act of organization immediately communicates competence. It tells the inspector you respect their time and you know what you're doing. It sets the tone for the entire inspection. Next, you go on a labeling safari. Every single component of the system needs a clear, professional, permanent label. The breaker and the panel that controls the exhaust fan? Labeled. The breaker for the makeup air? Labeled. The manual pull station for the fire system? Labeled. The gas shutoff valve? Labeled. I once saw a 7-figure restaurant project get a red tag, a hard fail, because the label on the fire system pull station was printed on a piece of paper and taped to the wall instead of being a permanent, engraved placard. The inspector's logic was simple. If they cut a corner on a $2 label, where else did they cut corners? Don't give them that thread to pull. Then you clean. I don't mean you sweep up the sawdust. I mean you clean the site like you're preparing for open heart surgery. Wipe down the stainless steel hood until it gleams. Make sure there's no debris inside the ductwork. Clean the rooftop around the fan. A clean site screams professionalism. A messy, chaotic site invites the inspector to look closer, to dig deeper, because it suggests the work itself might be just as sloppy. And finally, the most critical step, you test everything yourself. Don't wait for the inspector to find a problem. You find it first. Fire up the exhaust fan. Does it run smoothly? Is the vibration minimal? Turn on the makeup air. Does it activate in concert with the exhaust? Does it deliver the right amount of air? Now the big one. You perform your own test on the fire suppression system. You check the interlocks. When the system is tripped, does the gas valve snap shut instantly? Does the makeup air unit power down? Does the exhaust fan keep running as required by code to vent the smoke and suppression agent? You need to know with 100% certainty that every single component is working in perfect harmony before the inspector ever sets foot on your property. The day of the inspection, you're ready. You have your binder. The site is spotless. You've already tested the system. When the inspector arrives, you greet them, you're polite, you're prepared. You walk them through the job. You don't hover, but you're available to answer any question. They'll start with the hood itself. They'll run their hand along the seams, feeling for any gap in the liquid-tight welds. They'll take out a tape measure and check the overhang. Is the hood extending a full 6 inches beyond the cooking equipment on all open sides, as per code? They'll check the distance from the cooking surface to the filters. Too close is a fire hazard. Too far and you lose capture efficiency. They'll look at the filters themselves. Are they the correct UL-listed baffle type? Are they installed at the correct angle between 45 and 60 degrees from the horizontal? These are not suggestions. They are non-negotiable safety requirements. From there, it's a journey through the ductwork. This is where so many installations fail. The inspector will be looking for 3 things: material, construction, and clearance. The material has to be carbon steel of at least 16 gauge thickness or 18 gauge stainless steel. No flimsy aluminum, no galvanized steel that can't handle the heat or the corrosive grease. The construction is even more critical. They will check the welds on the duct. Are they continuous just like the hood? They'll shine a flashlight inside looking for any penetration, a stray screw, a bolt, anything that could snag grease and create a fire hazard. They will check for access panels. Code requires them at the top of every vertical riser and at the bottom of every vertical riser. They need to be within 20 feet of each other on any horizontal run and at every single change of direction. Miss one access panel and you fail. Period. Then comes clearance. This is the holy grail. 18 inches. That's the mandatory minimum clearance between your grease duct and any combustible material. Wood joists, drywall, anything that can burn. If you don't have that 18-inch bubble of safety, you must have a listed, factory-built, zero-clearance grease duct, which is significantly more expensive. Cheating on this clearance is one of the fastest ways to get your project shut down. Next, you go to the roof. The rooftop is a story all its own. The inspector will walk right up to your exhaust fan and grab it. They're checking for a hinge kit. The entire fan assembly must be on hinges that allow a service technician to tilt it back for cleaning and maintenance without having to lift a 300-pound fan off the curb. It's a safety requirement for the cleaner, and it's non-negotiable. They'll look at your grease containment system. A little coffee can filled with cat litter isn't going to cut it. They want to see a proper, UL-listed grease box or containment system that can handle the volume of grease your specific cooking operation will produce. Finally, they'll look at the termination point. The fan must exhaust at least 40 inches above the roof surface, and it must be at least 10 feet away from any property line or air intake for the building. This prevents grease-laden vapors from damaging the roof or being sucked right back into the building's HVAC system. And now the final boss, the fire system test. This is where everything comes together. The fire marshal may be present for this part of the inspection. They will ask you to perform a test. This usually involves cutting a terminal test link over one of the appliances. When that link separates, it's a chain reaction. A cable pulls, the system actuates, and a symphony of safety should erupt. They will watch with an eagle eye. Did the nozzles discharge correctly? Did the gas valve shut off? Did the powered appliances under the hood shut down? Did the makeup air turn off? And did the exhaust fan, the hero of the story, keep running? If any one of those things fails to happen in that split second, you have failed the inspection. If you pass, you get the coveted green tag. It's a sticker, a piece of paper, but it's so much more. It's your license to operate. It's the validation of every weld, every wire, every decision you made. It's the moment you can finally tell the owner, we're good to go. But what if you fail? What if you get a red tag? First, don't panic and don't argue. Arguing with an inspector is like wrestling with a pig in the mud. You both get dirty, and the pig likes it. Listen. Take notes. Ask them to cite the specific code section for each violation. They are required to provide this. You will receive a correction notice, a punch list from the city itself. This is now your blueprint for what needs to be fixed. You methodically work through that list, you correct every single item, and you document your corrections with photographs. Then you call for a reinspection. It's a delay. It costs money. It's frustrating. But it's part of the process. A failed inspection isn't a final judgment on your work. It's an opportunity to make the system even safer, even better. It forces you to adhere to the highest standard, which is the only standard that matters when you're dealing with fire. Because getting that green tag isn't the end of the story. It's just the end of the beginning. You've built a powerful, safe, and compliant system. You've proven it works. But now the real work begins. Now you have to keep it that way. The battle of installation is over, but the war of maintenance is just getting started. And so you stand in your kitchen, looking at this gleaming stainless steel beast you've just wrestled into existence. It's past inspection. It hums with power, feels finished. But that feeling is a lie. It's a dangerous illusion. Because the moment that first sizzle hits the grill, the moment that first plume of greasy smoke is captured and pulled away, a silent enemy is born. It's an enemy that never sleeps, never stops, and is relentlessly plotting a catastrophic failure. That enemy is grease. Think of it like this: your exhaust system is the artery of your kitchen, and grease is the cholesterol. First, it's an invisible film, a microscopic layer. You can't see it, you can't feel it. But with every single burger flipped, every basket of fries dropped, every steak seared, that layer grows. It multiplies. It transforms from a liquid oil into a sticky, semi-solid sludge, and then over time it bakes into a hard, flammable crust. It's a ticking time bomb, coating the inside of your entire system. From the filters you see to the deepest, darkest corners of the ductwork you don't. This isn't just a cleaning issue. This is a fuel source patiently waiting for a single spark. And in a commercial kitchen, sparks are not exactly in short supply. The war of maintenance isn't won with one big heroic effort. It's won through relentless, disciplined, daily vigilance. It's about shifting your mindset from project to process. Installation was a project with a start and a finish. Maintenance is a cycle that never ends. And the first line of defense in this war isn't a professional cleaning crew. It's your own kitchen staff. We begin with the daily ritual. This is non-negotiable. It needs to be as ingrained as washing hands. At the end of every single shift, the exterior surfaces of the hood must be wiped down with a food safety greaser. This isn't just for looks. It prevents a sticky film from attracting dust and grime, creating an insulating layer that can mess with the hood's performance and become a fire hazard in its own right. Next, and arguably the most critical daily task, is checking and emptying the grease traps or cups. These little collection boxes are the system's first catch point. If they overflow, you have a river of hot grease running down your wall, onto your cooking equipment, and potentially onto the floor. It's an instant fire hazard and a massive slip and fall liability. This takes 30 seconds. 30 seconds to prevent a disaster. Finally, the daily ritual ends with a quick visual inspection of the baffle filters. Are they seated correctly in their channels? Is there any visible heavy dripping? This quick glance can tell you if you're on the verge of a major grease buildup problem. Once a week you escalate. This is the weekly deep clean. This is where you pull the enemy out by the roots. The baffle filters must be removed and thoroughly cleaned. And I don't mean a quick rinse. They need to be submerged in a deep sink filled with hot water and a powerful commercial degreaser. Let them soak. Let the chemicals and the heat do the heavy lifting, breaking down that polymerized grease. For stubborn buildup, a stiff bristled brush or even a pressure washer can be used. Clean filters are the gatekeepers of your system. When they're clogged, airflow is restricted. The fan has to work harder, pulling more electricity and shortening its own lifespan. Smoke and heat spill back into the kitchen. Clogged filters are a sign of a system gasping for air. But here's the secret most people miss. After you clean the filters, you must clean the channels they sit in. The plenum, the area directly behind the filters, is a forgotten grease trap. Scrape it out. Wipe it down. If you put clean filters back into a filthy plenum, you've only done half the job. Now we move to the monthly inspection. This is where you go from being a cleaner to a technician. You're looking for signs of wear and tear. The number one component to check is the fan belt on your exhaust fan. Over time, belts stretch, crack, and lose tension. A loose belt will slip, meaning your fan isn't spinning at its designated RPM. You're losing suction power, but you're still paying for the electricity. A worn, cracked belt is a failure waiting to happen, and it will always happen during your busiest dinner rush. You can check the tension easily. With the power off and locked out, you should only be able to depress the belt about an inch in the middle. Anymore, it's too loose. Look for fraying or cracks. A new belt costs a few dollars. A new motor or a restaurant full of smoke costs thousands. While you're up there, check for any manufacturer-recommended lubrication points on the fan motor bearings. A little grease now prevents a catastrophic seizure later. This brings us to the most important part of the maintenance war: the professional offensive. This is not a DIY task. This is where you call in the certified special forces. According to NFPA 96, the National Fire Code standard, your entire system, from the hood to the termination point on the roof, must be professionally cleaned and inspected at a set frequency. This frequency depends on what you cook. For solid fuel cooking like charcoal or wood-fired ovens, it's monthly. For high-volume 24-hour operations, it's quarterly. For a moderate volume restaurant, it's semi-annually. And a professional cleaning is not just spraying some chemicals. It's a top-to-bottom, inside-and-out deep clean. A reputable company will wrap your equipment in plastic, get inside the ductwork with scrapers to remove the baked-on creosote, and then use high-pressure, hot water steam cleaners to wash every square inch of the system, funneling the wastewater into collection drums. They will clean the fan blades, the housing, everything. Beware of the splash and dash cleaners. These are companies that show up, clean only what you can see from the kitchen, and leave the ductwork, the real fire hazard, completely untouched. They'll give you a cheap price and a worthless sticker. Always ask a potential cleaning company for their process. Ask if they clean the entire duct run. Ask if they provide before and after pictures. Ask if they are certified and insured. When they're done, they should provide a certificate of cleaning with the date and the name of the technician. This sticker, usually placed on the hood, isn't just for show. It's your proof to the fire marshal and your insurance company that you are doing your due diligence. In the event of a fire, the first thing an investigator will look for is that sticker and the associated report. Without it, your insurance claim could be denied in a heartbeat. But maintenance is more than just fighting grease. It's about the health of the entire mechanical system. You need to learn to listen. Listen to your fan. Does it sound different today than it did last week? A new whine could be a failing motor bearing. A rattle could be a loose panel or a failing belt. The sounds are early warnings. And don't forget the other side of the equation: the makeup air unit, the lungs of your kitchen. Its filters get clogged with pollen, dust and city grime. When the MUA filters are clogged, you're starving your kitchen of air. This creates powerful negative pressure. You'll feel it when you try to open the front door and it feels like a vacuum is pulling it shut. Back-of-house doors might slam shut on their own. Most dangerously, this negative pressure can snuff out the pilot lights on your gas equipment and even cause your gas ovens to backdraft carbon monoxide into the kitchen. MUA filters are cheap and easy to replace. Do it regularly. Finally, there's the guardian angel of your kitchen, the fire suppression system. This is another area that is absolutely not DIY. It must be inspected and tested semi-annually by a licensed and certified company. They will check the nozzles to ensure they aren't clogged with grease. They will check the tension on the fusible links. They will test the pull station. They will verify the date on your suppression tanks. This is a life safety system, and its maintenance is mandated by law. The secret weapon that ties all of this together is a simple, humble logbook. Keep a binder in the manager's office. Every time a maintenance task is performed, write it down. Date of filter cleaning. Who did it? Date of fan belt inspection. Notes on its condition. Staple the receipt from your professional hood cleaning service inside. This logbook is your proof. It's your operational Bible. It creates accountability and turns a chaotic list of chores into a disciplined, repeatable system. You see, a commercial kitchen hood system isn't a machine you buy. It's a living system you must manage. The war against grease, heat, and failure is a forever war, fought with discipline, vigilance, and a deep understanding of the enemy. You've learned how to fight the daily battles, how to plan your weekly campaigns, and when to call in the special forces. But what happens when, despite your best efforts, the enemy breaks through your lines? What do you do when the system fails catastrophically at 7 p.m. on a Friday night? In our final part, we'll turn you from a soldier into a field commander, ready to troubleshoot any crisis and handle any failure the kitchen throws at you. The first rule of command is this: when chaos erupts, you don't rise to the occasion, you fall back on your training. So let's train. It's 7 p.m. on a Friday. The dining room is packed. Suddenly, the air in the kitchen gets thick, hazy. The familiar roar of the exhaust fan has been replaced by a sickening silence, or worse, a grinding metallic scream. Your line cooks are looking at you. Panic is a fire that will burn your business to the ground faster than any grease flare-up. You are the commander. You do not panic. You act. Your first move is triage. You need intelligence and you need it fast. Engage your senses. What do you see? Is smoke billowing from the grill but just hanging there, refusing to enter the hood? Or is it being pulled in but then slowly creeping back out like a reluctant ghost? What do you hear? Is it dead silent? That points to a total power failure. Is it a high-pitched squeal? That's likely a fan belt. A low grinding rumble? That could be motor bearings on their last legs. A loud, repetitive clanking? Something might have come loose and is hitting the fan blades. What do you smell? Is it just the smell of smoke? Or is there an acrid electrical burning smell? That's a motor overheating, and it's a critical warning. Before you do anything else, you walk to your electrical panel. Find the breaker for the exhaust fan and the makeup air unit. Is it tripped? More than half the time, this is your problem. A momentary power surge, an overloaded circuit. If it's tripped, flip it back once. If it trips again immediately, do not touch it again. You have a serious short and you need an electrician, period. Trying to force it is how you turn a $500 repair into a $5,000 fire. If the breaker is fine, your investigation moves to the roof. Your primary suspect is the exhaust fan. This is the heart of your entire operation. A safe ascent is paramount, but once you're there with the power safely locked out, you become a detective. Look at the fan belt. A healthy belt is tight and pliable. A dying belt will have visible cracks, a shiny, glazed look on the sides, or excessive slack. Here's a pro-level field test: the dollar bill test. You should be able to slide a dollar bill between the belt and the pulley with some resistance. If it slides in and out with no friction, your belt is too loose. It's slipping, not turning the fan at full speed, and it needs to be tightened or replaced. If you can't get the bill in at all, it's too tight, which will destroy your motor bearings. While you're looking at the belt, put a hand on the motor. Is it excessively hot to the touch even though it's been off? That's a sign it was struggling. Give the fan blades a spin by hand, again with the power off. Do they spin freely and silently for a few rotations? Or do they grind to a halt with a horrible noise? That grinding is the sound of failing bearings. You've found your culprit. That sound is a countdown clock. It might last another month, or it might seize up in the next 10 minutes. That's a call you need to make to your HVAC tech tonight. Now let's consider a different scenario. The fan on the roof is roaring like a jet engine, but back in the kitchen, the air is still heavy. This isn't a problem of extraction. It's a problem of replacement. Your makeup air unit isn't doing its job. The kitchen is pulling a vacuum, and the exhaust fan is fighting against a sealed room. Your first and most likely suspect here are the filters on your MUA. When were they last changed? A clogged filter is like trying to breathe through a wet towel. It suffocates your system. If they're caked in dirt, pollen, and grime, you've likely found your issue. Swapping them out might just solve your entire problem. If the filters are clean, you could be looking at a failed sensor or a problem with the control interlock that's supposed to turn the MUA on with the exhaust fan. This is where you move from field triage to calling in specialized support. But knowing the difference saves you from a vague, panicked call to your technician. Instead of saying, "My hood's broken," you can say, "My exhaust fan is running at full speed, but my MUA isn't kicking on and the filters are clean. I suspect an interlock or sensor failure." You just saved hours of diagnostic time and potentially hundreds of dollars. You sound like a professional and you'll be treated like one. Now for the worst case scenario. A sudden loud pop, followed by a whoosh of white or gray chemical. Your fire suppression system has discharged. The first thing to understand is that this is the nuclear option. The system did its job or it had a catastrophic failure. Either way, your kitchen is now offline. Do not pass go. Do not collect $200. Your immediate actions are critical. Step 1. Kill the main gas valve to your cook line. Step 2. Kill the power to the appliances. Step 3. Get everyone out of the immediate area. While the chemicals are generally non-toxic, they can cause respiratory irritation. Step 4. You call your certified fire suppression service. Not tomorrow. Now, this is not a DIY fix. Attempting to reset the system yourself is a violation of fire code in almost every jurisdiction and can lead to a catastrophic failure when you actually need it. The technicians will need to replace the fusible links, recharge the cylinders, and recertify your entire system before you can legally and safely operate again. Your job as the commander is not to fix it, but to manage the crisis, secure the scene, and get the right experts on the line immediately. These are the reactive, in-the-trenches tactics. But the true secret to mastery, the way you win the war, is to make sure you never have to fight these battles in the first place. It's about shifting from a reactive soldier to a proactive strategist. This is accomplished with a simple, non-negotiable ritual: the 5-minute pre-flight checklist. Every single morning before the first burner is lit, you or your kitchen manager does a walk around. You stand under the hood and you just listen. You know what your system sounds like when it's healthy. That smooth, consistent roar. Any new sound, a tick, a squeal, a hum, is a piece of intelligence. It's your system telling you something is wrong before it fails. You look at your fire suppression nozzles. Is there a heavy coating of grease building up? That's a fire hazard and a sign your regular cleaning isn't thorough enough. You check your MUA filters. You glance at the tension on the fan belt. You keep a logbook, a simple notebook where you write down the date of every professional cleaning, every belt replacement, every strange noise you hear. This logbook becomes your system's medical chart. When a technician arrives, you don't just shrug your shoulders. You hand them a detailed history of the patient. This turns a guessing game into a surgical diagnosis. And when it comes to choosing those technicians, your allies in this war never ever choose based on price alone. A cheap hood cleaner who just gives it a quick surface spray is worse than useless. They give you a false sense of security. Your professional cleaning and maintenance company should be an investment in your survival. Ask for proof of insurance. Ask if they are certified and if they follow NFPA 96 standards to the letter. Ask them to provide before and after photos of their work, including inside the ductwork, not just the parts you can see. A true professional will be proud to show you their work. A cheap operator will make excuses. Because in the end, that's what this is all about. This entire system, this complex assembly of steel, fans, and pipes, isn't just a piece of equipment. It is the silent, sleepless guardian of your business. It protects your staff from a toxic work environment. It protects your building from a fire that could destroy everything you've built. And it protects your customers, who trust that the meal you're serving them was prepared in a safe, professional kitchen. Mastering this system isn't about becoming an HVAC technician or a fire marshal. It's about adopting a mindset of ownership. It's about understanding that the secrets to effectiveness aren't hidden in some obscure manual. They are written in the daily hum of your fan, in the cleanliness of your filters, and in your unwavering commitment to vigilance. You are the commander of your kitchen, and with this knowledge you are now equipped not just to face the battle, but to win the war before it even begins.